Greetings. This is the first video I'll be making in a series on topics related to control surveying, and this first one will be specifically on meeting the positional accuracy standards for construction and mapping projects involving 3D laser scanning, mobile LIDAR, and UAV mapping. And specifically, this presentation will cover the combination of GNSS vectors, digital leveling observations, and 3D total station measurements to establish survey control points and targets. My name is Jesse Kozlowski. I'm a licensed land surveyor in New Jersey. Now, I have a lot of slides to go through. I do not want to make a very long, boring video. I'm going to try to move through this quickly. And the next two slides I hope to capture your interest. This is just a preview of the presentation. I'll go into greater detail later in the presentation as to what all this is, and this is the one that I hope I really capture your interest right now to stick with me. Mistaking precision for accuracy will hurt you, and that is going to be the primary topic covered here. A little bit about me. Again, my name is Jesse Kozlowski. I've been surveying for, well, about 40 years now. Here's just a little bit about my bio, and most of my career has been spent doing control work for all sorts of projects, large and small, and so that's kind of my specialty, and that's what I'll be talking about in this presentation. So what I'll cover today is really applicable to lots of disciplines, whether it's highway involving bridges and tunnels, or railway transportation, again, lots of tunnels and bridges, energy transmission and generation in power plants and utility lines, and pipelines for gas and oil, and of course building infrastructure. Everybody that is involved in these various disciplines all rely on survey control to get their projects completed. All right, let's take a quick look at targets and control points. They're going to be different depending upon the application. You may have seen these types of spherical targets on your projects for 3D laser scanning, or for mapping projects you may have seen these black and white checker patterns with a number, and sometimes they're painted in the roadways for aerial photography or UAV mapping. And then this type of a chevron target is used in mobile mapping applications quite a bit. It could even be the simplest thing as a checkerboard paint printed on paper, taped up on the wall. And now we have even these targets made by propeller that actually log GPS, GNSS data, and these are used in UAV quite a bit. Then you've got the good old-fashioned large panel for a mapping project being located by GPS. Here we are just looking at a point cloud, 3D laser scanning point cloud in a rail situation, a tunnel situation, and we could see over on the right side just a couple of targets taped up on the columns. And then of course the new smiley face target. Okay, in the next slide I'm going to introduce a common QAQC problem. Let's take a look. We have some point cloud data here, and we're comparing our coordinates for that target, and we see deltas, that is differences. Over here on the chevron we have some mapping digital photography, the coordinate of the chevron is different than the control value. And the amounts of these differences are larger than expected, or possibly just entirely unacceptable. And so in a nutshell, what we're saying is that the control points do not match the point cloud as expected. So what is the expectation? Well, it has to be as accurate as possible. You may have heard people talk like this. It has to be perfect. And there's no room for error. Or they'll say it has to be within an 1/8 inch. The contract specifies 1/16 inch tolerances, or 32nd inch accuracy, or it has to be second order. Alright, so here we have various expectations. Let's talk about these a little bit. In my mind, these are just imaginary because there's actually no such thing as perfect values. And I hope to get that across through this presentation. These other ones, while they are at least better than the the first three, still there is the need to verify that you've obtained these specifications. So, and when you haven't, then the situation becomes one where people are pointing fingers at each other. And you know, how do you go about verifying that you've met these specifications? So I'm saying that these are all ambiguous, and that this is where the problem actually starts. And then as far as second order, who even knows what that means anymore? So I want to take a look at that. Okay, so before I talk about what second order is, I want to make a distinction right now, right up front, between point cloud registration versus project datum reference. You're probably already aware that the technology is advancing to the point now where each setup of the scanner is being registered in real time in the field. So you're getting your point clouds registering together, but that's different than registering those clouds to the datum. That's something else, and that is what we're talking about in this presentation. So just to illustrate that, we're talking about the project datum and the designed alignment so that the cloud and imagery is matching the control points on that project. Okay, so with that distinction made between registering point clouds together and aligning those clouds to the project datum, let's get back to the QAQC problem that I'm presenting here, where again the control points and point cloud do not match. Okay, and we're going to continue with this idea. So there are a variety of possible causes to this. Okay, you could probably start thinking of some in your own experience, but no matter what the cause is, things come to a screeching halt. Like I said, there's finger pointing. This has to be resolved before you can continue. So there's an easy solution to the most common cause, and that's what I'm going to focus on through the rest of the presentation. And by the way, what I'm going to show you has to happen no matter what anyway. What I'm going to show you in this presentation you have to begin with it before you can even start to explore the possibility of any other causes. So, but the fact is, most often what I'm going to show you here eliminates the problem immediately. And so I'm just trying to keep your interest. Stick with me. I can't tell you the whole thing in the first two slides. So here we go. So back to this examination of the expectations, and I told you we're going to look at second order, and this is going to kind of give us a kind of a history too of where things were in the past and how it is we get to where we are today. And even though technology is changing rapidly, the fact is a lot of things remain the same. The common basics still apply. So let's keep that in mind. Okay, so back to our very brief history lesson, taking a look at what second order is, where that came from. I'm saying it's old school. You can look at this document from 1974, and as you look in here, you're going to see orders of accuracy: first order, second order, and third order, and the classes below those. Lots of people think of just closure only. Oh, they've met first order because they closed in greater than 1 part in 100,000. There's more to it than that, and so it's actually a prescriptive standard. It's not just the closure that you meet. It's actually specifying the types of equipment to be used, the number of repetitions to be taken, observed. So it tells you how to do the work in order to meet that order of accuracy. Now these prescriptive standards made it into lots of the DOT manuals along the way. I'm just showing you a sample of some of them that I downloaded from the internet. Not all 50, but just some of them. And I like this last one from Arizona because it kind of captures everything we're talking about from this huge aerial panel and GPS involved, and then 3D laser scanning. These standards also made their way or are part of the Army Corps of Engineer manuals, the USACE manuals. Take a look. You can get these on the internet as well. And again, it's a prescriptive standard. Second order is meaningless unless you are actually looking at, it's not just a second order closure, it's second order procedures. You have to look at all of it, way beyond the time I have to go into in this presentation. And there's other standards. Recently I was asked to perform a survey in accordance with a BOMA standard. I was not even familiar with it. So this is a specific standard related to buildings. All right, so with that little bit of history out of the way, we're going to jump into the bulk of this presentation involving positional accuracy standards. So these are positional accuracy standards, not closure, relative closure standards. Let's take a look. If you look at the page 2-3 of this publication by the FGDC, and actually this was published in 1998, but it's really becoming, so a lot of the state DOTs are actually starting to incorporate this standard now too, with the recognition that we're not doing things the same way all the time anymore, and this standard is actually preferable for doing control work, especially in this modern era of using 3D laser scanning and so much digital imagery. So what you'll see on this page 2-3 is just a table of accuracy specifications, positional accuracy specifications at 95% confidence. Let's zoom in on that a little bit. And that's it. And this is not a prescriptive standard. You won't find anything in this book telling you you have to make your measurements this way or that way, or you have to use this type of piece of equipment. It's not that way anymore. About the only thing prescribed is how to handle the data, the fact that it must be analyzed, and there are certain things you have to do, which I'm not going to cover right here, but that's about the only prescription you could say is there. This is a more flexible way of doing our survey control work. and it accommodates a lot of the technology we have at our disposal now. So I've been seeing some discussions on LinkedIn about where we are today with trying to get people involved in surveying. Some people complain we have a lot of button pushers, which I really feel is unfair, because anybody that's involved in surveying now, that is just getting involved now, does not have the luxury or the afford the time that we've had in coming up through the profession as a rodman and then an instrument man and then a party chief. Those days are gone. I mean, we had a longer time to learn the profession. So it's up to us to help and mentor those who are coming in now and try to catch them up a little bit. This is a great book, and I'd recommend it to anybody that is interested in survey control and the measurements involved in land surveying, by Ben Buckner, the survey measurements and their analysis. I'm just going to kind of pull one thing up here from chapter 9, the surveyor as expert measurer. He says here, many surveyors will arbitrarily select equipment and methods, then merely hope that the tolerance is achieved, blindly relying on the precision of the equipment. These surveyors will certify to the accuracy, rationalizing that they had done their best. So the fact is, the equipment we have available today is incredible. I mean, if we can just manage to get it set up over the right point, you're going to end up with incredibly precise measurements. All right, so we have to go beyond that, though. We have to actually handle the data, and we have to analyze the data. We have to assure that the results are where they need to be, that we've actually achieved the goal for the project. So again here, instead, the professional approach includes a thorough design of the measurement specifications to achieve the required accuracy for the project application. So what I'm going to go into now is a presentation of some data and discussing this whole accuracy versus precision thing. And you've seen this topic covered so many times. I'll just show you my take on it, and I'm going to be using, and it's going to be a real-time network VRS example. Could easily also apply to an RTK base station and rover. So we have here a Trimble R10 set up over a point out in front of the office. All right, just to cover this quickly as a bit of review before we get into looking at the data I'm going to show you. We've all seen this bullseye target scenario or example. So what we have here on the left is let's get this thing working. Yeah, there we go. So we have the example of very high precision, but no accuracy there. Then the next one is low precision, but the average there gets you an accurate result. That next target over is you have nothing. And what we're after is the target on the right. We want to take that equipment, operate it properly, and use the appropriate care to assure that we end up with accurate results. The one on the far left is the example of using this incredible equipment and possibly not taking the care needed, or making blunders that should have been detected, and you have high precision measurements, but they're nowhere near achieving the accuracy needed. So boom, I'm just going to leave that there. Distinction between accuracy versus precision. So the data that I'm going to be showing you, it's just collecting some VRS data in the morning. I got nearly 3 hours. I got 2 hours 50 minutes of data, and I had the equipment set up to log a position every 30 seconds. So we ended up with 342 observations. And then in the afternoon, I got just over 2 hours, about 2 hours and 16 minutes of data, and that ended up giving us about 250 observations, again at a 30-second epoch. And all totaled, between the morning and the afternoon, we have 6 hours and 41 minutes of data. Alright, so next we're going to take a look at some graphical display of the data. We're going to look at the elevations actually. Here's a plot of the data collected in the morning, and we have elevations in feet on the left on the y-axis, and on the x-axis it's time, and the blue dots represent 30-second intervals, just a shot recorded every 30 seconds. And here are some of those elevations just over the course of that time period. And what you're looking at here is the peak-to-peak range of 4/10. And there's the average. 41.25 feet was the average elevation out of this whole data set. And next I'm showing you the band representing the standard deviation, which is turned out to be 7/100ths of a foot plus or minus, and that is 1 sigma. So that's 68% of these observations fall within that band. And for a higher confidence, we're looking at plus or minus 14/100ths, and that gets you 2 sigma, which is a 95% confidence interval. And there's the data again, showing you the max, min, and the range, and the standard deviation. Now let's look at the afternoon. There's our average is 41.20. There's our peak-to-peak range of almost 5/10 in this case. These orange dots are again 30-second epoch recordings. And again, looking at the standard deviation, it's in this data set it turned out to be 9/100ths plus or minus, and which is a 1 sigma, and bumping that up for a higher confidence, what we're saying is that you should be able to repeat and be inside of this band at 95%. In other words, if you go here 95 times out of 100, you should end up with an elevation inside that range there. And again, there's a close-up of that tabulation. So when you look at that, I hope you now get what I'm saying here, that mistaking precision for accuracy will hurt you. When you look at your data collector, let's zoom in there, and you see 100th by 200ths, horizontal and vertical. And you think that what you're doing right there is accurate to those numbers. You're mistaken. And basically these values are the precision of the system performing at that moment. You're seeing that type of repeatability at that moment, and they're being reported to you at 1 sigma, which is 68% confidence. And I'm showing you a Trimble data collector here. This would apply to any manufacturer. They're not doing anything different. This is how RTK works. And then just before we move on, just a reminder again of the difference between accuracy versus precision. So the data we just looked at We were just set up on a random point. We really couldn't say anything about the accuracy. We were just able to examine the performance of the system just by setting it up on a random point and then doing some statistical analysis on the data collected. And we find that the system performs exactly as stated in the manufacturer's brochure. If you flip over the brochures of any of the manufacturers, they're going to tell you how the system performs and what its precision is, or its RMS it's going to say, and they're usually reported at 1 sigma. Next, we're going to look at doing the same type of test and having a point to compare to. So in this case it's station HAINESPORT, which is a deep rod mark. There it is. It's a deep rod mark set to refusal, and was published in 2006. And here is the Trimble R10 receiver set up over that mark. And here's the data sheet for the mark, and some field notes just indicating the date of the collection. Again, 30-second continuous topo, and also recording the raw data, and the start and stop time. So over here on the data sheet, you could see that they report the positional accuracy just the way it is described in the book, in the standard book, the FGDC book I showed you earlier. So here's just a quick presentation of the data. This was not a morning and afternoon, it was just one long occupation, and it was about almost 5 hours and 20 minutes about. So we ended up with 639 observations at a 30-second epoch, and I also sent that data to Opus. Okay, so now let's take a look at this data plotted graphically. Let's see what we have here. This is the VRS average elevation. This is the elevation that Opus reported back, and this is the published elevation. The peak-to-peak range over the 5 hours and 19 minutes was almost 3/10. And again, what's the expectation? Read the data sheet. I mentioned this earlier. You can take the data sheet for any piece of equipment and look at what the manufacturer is telling you you can expect in terms of performance. So in this case, this was a network RTK, and the expectation in the vertical is 15 millimeters plus 0.5 parts per million, and that's reported at an RMS, and that would mean that it's 68.3% of the time. Okay, so let's plot that. Here we see the 1 sigma value is, in this case, plus or minus 5/100ths of a foot. So there's the 1 sigma, and at 2 sigma it's plus or minus 1/10 of a foot. 2 sigma. Did we make it? Well, if we take the 15 millimeters plus the 0.5 parts per million, we see that we should be performing at 1 sigma within about 7/100ths, and we see that we are. So the system is performing well within the tolerance specified. Let's look at this data a little bit more. So here we have the peak-to-peak range in the elevations as almost 3/10 of a foot. And let's look at these 3 times. I almost said points. These are not points. We're occupying one point called HAINESPORT. These are just 3 portions of time, A, B, and C. Now keep in mind the data collector screen that I showed you earlier, where you're looking at the precision, is 1/100th of a foot horizontal, 2/100ths of a foot vertical, and that's at 1 sigma. That would be as though you were occupying point HAINESPORT during the time circled there with labeled A. And let's just say you were observing that for 180 epochs to resolve a position there as a control point. All right. And then you left and went and did some other work, and you came back later that day, and let's say at a point in time labeled B, and you did the same thing. You can see that the positions that you would determine there between A and B would be an elevation difference of possibly 2/10ths or so. So some people get really alarmed when they see that, and that's because they're not acquainted with the performance specifications of the equipment they're using. That's not alarming at all. That's actually to be expected. To even make things worse, people who just shoot things with like 1 epoch or 5 seconds, you can see that, recall that we are looking at in the blue band. The blue band is 95% of the time. That means that there's 5% of the time that you could go and hit that point and hit it again later and possibly be as much as 3/10ths different in elevation. That's not alarming. That's just how it works, and I've said that earlier. This is how RTK works. And so let's look at these points again, A, B, and C. You could go there and observe HAINESPORT and get your position on A at time A. Come back later and observe it again at time C and resolve that position and find that you have agreement at a couple of hundredths level, but you're pretty far from the published elevation. And whereas if you did A and then did time B, chances are the average of those would be closer to the VRS average or even the published value. You can see that the OPUS value and the published value are only 1/100th apart. That's pretty amazing. You don't always see that either. So this graph really gets across the idea here that you really need to be paying attention to the difference between precision and accuracy, and build into your methods and procedures ways of getting accurate results with that incredibly precise equipment. That's a mouthful. I think that sums up this slide. Let's move on. And speaking of methods and procedures designed to achieve accuracy, an accuracy specification, take a look at Mark Armstrong's presentation he did, and this is dated 2013. Go look this up. It's an excellent resource to go through, and going through this entire topic of precision versus accuracy using RTK. So I'll just leave that there for you to go find for yourself and take a look at. It's very valuable. Okay, moving on. Now back to the main topic in this presentation, this common QAQC problem where the control points do not match the point cloud as expected. We're about a half hour into the presentation. I hope you've stayed this long. We're really going to get into some interesting stuff coming up. Stick with me. It'll be well worth your time. So just to remind you, what we're seeing is a situation where the control values are not matching either the point clouds, the imagery, or in some cases actual construction elements on the project. So continuing, we're going to examine the problem now, and first by just looking at something very common. It's your typical text file that you'll receive or generate, and this happens to be a comma separated text file of ASCII information. Let's take a look at it in Excel so we can look at it a bit easier. So we have columns here of point numbers, northings, eastings, elevations, and point descriptions, such as some control points and targets. So the big question here is the positional quality indicated in this file? And the answer, of course, is no. So this can be a problem, and that's what we're going to explore next. So here's how I'm suggesting to solve this problem. I'm saying there are 3 columns we should be adding to a survey control file, and these are the standard deviations of the points, the north, the east, and the elevation, and in this case these have been scaled up to a 95% confidence level. Insist on receiving the positional accuracy of the control points and the targets. So when you have that information as the last 3 columns, you are better equipped now to make an evaluation or a determination of how consistent this control is. Does it meet your expectation? Does it meet the goals for the project, the accuracy goals for the project? Have these points all been leveled through? Were they supposed to be leveled through? Does anything stick out that might indicate a problem? That type of evaluation can be made right away just by sorting the columns by largest value. You can see anything that might pop up. So let's take a look at just an example, bringing back into the discussion here the book that I had shown you earlier, the 1998 publication, which includes the table of positional accuracy values. Let's take a look, and here's the last 3 columns from the sample data that we're looking at here. And let's just say the project specification called for a 2 centimeter accuracy. I should also say that you can specify a certain horizontal accuracy and a certain vertical accuracy. They don't have to be the same, but just for a simple discussion here, we could see that some of these points excuse me, stick out a little bit more than others. That third point down, or actually the easting of the second point down, is almost 8. And I'm not including units here. I'm not trying to goober this up with feet or meters. Just look at the values right now. You're able to make a determination right away, the points that meet and the points that do not meet. And then you can make a decision about, well, what is that point? Is it just squeaking by slightly, or do we have a real problem here? Maybe we have to go reobserve that, or drop it from our solution. All I'm saying is you're able to make a determination right now, instead of during the LIDAR processing when that's like the last place you want to be making these types of discoveries. This is part of the QAQC process. It should happen before the control values are given to anyone else to use for additional processing of LIDAR data or of construction layout, etc. So hopefully that makes a lot of sense to you. Again, I just want to reintroduce another segment of Ben Buckner's book, Surveying Measurements and Their Analysis. And I'm doing this because I want people to kind of get back to some of the basics, some of the things we kind of don't think about anymore because we're just using electronic equipment, and we buy it, we put it out there in the field, we use it, and we're forgetting that that equipment is still affected by things like this. I mean, this matters. Horizontal refraction affects horizontal angles. The bending of a sight line can occur when the sight line passes very closely to large objects, such as buildings, especially if they are radiating heat. This can cause an erroneous pointing. So again, we have to get back to thinking about what we're doing. Let's say you're down in a tunnel and you're trying to make these observations, and there's some equipment down there. Maybe there's a piece of equipment running, and heat exhaust is coming across the line of sight. Yeah, you could wrap that angle 8 times or 16 times. It doesn't matter. You're going to have an erroneous pointing. So you have to still think about what you're doing, even though we do have this magnificent equipment able to make incredible measurements and record them for us. We as surveyors are still involved in planning that project, executing it, and making sure everyone involved, the field staff, the surveyors on the job, are acquainted with these all these principles and these aspects. So, propagation of random errors in horizontal angles. Estimation of expected closure and evaluation of uncertainty is an important part of surveying measurement theory and practice. Such ability elevates the surveyor from craftsman or technician toward professional status. This is good stuff. We should keep it in mind. We are not button pushers. We are not just collecting points and exporting them to somebody and say, hey, it's good. Why? Because I have a 1-second robotic total station. I don't think so. It doesn't work like that. So you want to develop a control plan. You want your people to know where they should be putting these points. And again, you're going to look at the site conditions and try to plan the best route. If you're going across a bridge, well, you've got to think about that. How are you going to cross that bridge? Are you doing digital leveling or not? What does the project call for? That's going to indicate what equipment is needed and what methods and procedures are needed. Just don't go out and shoot stuff. We got to get away from that. Shoot that. Go out and shoot those points. So here, let's look at surveying measurements. I'm including this too for anyone that may not be a surveyor but kind of heard about this presentation and became interested in this topic. So in a nutshell, we've got surveying measurements like these. We have radial RTK or RTN vectors, and generally a lot of aerial control is being located using that method, and it's probably fine for that method. Keep in mind, I showed you earlier in the presentation the type of a deviation or difference you can see in the elevations. You got to look at your project specification to make sure that the level of mapping you're doing can absorb that. If it can't, you've got to think about other ways of tightening that up, let's say. So of course some projects can't tolerate 2/10 of difference in elevations between points, and so you may be using some RTN vectors or post-process vectors from cores, and then also some vectors between the points on the project site. So here would be a simple little network of GNSS vectors tying the site and tying points together on the site. And now we're using a total station to supplement and put in additional control or surveying targets on the project. And then some projects require very, very tight vertical accuracy, and in that case you're going to break out that digital level and run through a lot of the points, if not all the points. Depends on the job. So where do these last 3 columns come from? How do we get these columns? We're not talking about exporting out the precision from the data collector. You can do that. And of course, by now in this presentation, I hope you do recognize that that is not what we're talking about in these last 3 columns. The precision of the measurements is not an indication of the accuracy. I can't say it too many times. The last three columns indicating the positional tolerance of the points comes from surveying analysis software. Dare I say it, least squares adjustment software. Has anyone ever, if you ever used some of the NGS software available, you can, everyone's familiar with StarNet, and there's Columbus, and I've used both of these. And dating myself, I go back to TrimNet Plus days. I love that software. It's yeah, it's great software. Anyway, I'm just getting nostalgic there. Of course, using Trimble Business Center now, and Carlson has ServNet, and I've used that, and it works very well. And I love Move3 as well. And of course, other manufacturers produce their own least squares analysis software. So the positional accuracy comes from the least squares adjustment. And that is how we can determine that all of these control points are related to each other. None of them have just been keyed in. They weren't keyed in from Google Earth. They are all consistent, and you know, you're going to know right away. Did you level through all of them or not? Do you have duplicate point numbers that are next to each other and are really supposed to be the same point? And then, you know, you by chance grab the wrong value, the point that wasn't leveled through. There's so many blunders that can occur that if we take the time to take the care in the field, collect the data correctly, and then bring it in, eliminate those blunders, and perform a least squares adjustment, you're going to end up with very, very reliable control. And basically that's what this page is indicating, that you're going to be doing a minimally constrained adjustment, and then you're going to do a fully constrained adjustment, which really matters if you're doing control on site, in a plant, factory, in a setting where you have to be that your new survey work has to match into legacy control. This is the only way you're going to be able to make that happen in a way that provides consistent results. So no adjustment, no positional accuracy. Therefore, the control values are really in question. And this really is, we're getting close to the end of the presentation. I'm glad you stuck with me this far, because this is where I'm going to really make the point. Unfortunately, this happens a lot. These types of text files are even sometimes just exported right out of the data collector without any analysis and given to someone else to make use of. And then they struggle with it, and they wonder, why are we missing this by a couple of tenths here or there? Or if it's maybe under a tenth, they just say, well, I guess that's how it is, and go on. And that's unfortunate, because if you take the time, and it's not a lot of time spent, you just, you know, you get good at doing it, you can produce results that are fantastic. And when you give them to someone else, it's all going to match, and everyone's happy, and the project moves on. There's no pointing fingers and you know, questions about, you know, is the LIDAR bad? Is the control bad? What's going on? Let's do that QAQC up front before we get to a problem like that. So don't jeopardize the project. Insist on results from the QAQC of the raw survey observations. That's what you want to see, is that everything on the site is consistent. So if you want to guarantee a problem, then export out this file right out of the data collector. You know, you've already seen what happens. Everything looks great. No matter what time of day, you're going to be seeing 100th by 200ths and that's precision, not accuracy. So so on that site, if you surveyed that site all day long, you'd be real happy if the elevations on that site were within 2 or 3 tenths, and that's for sure. And you know what I'm talking about. You've seen this. So you put in a couple of RTK points or VRS points on one side of the project, and then later on in the day you put some elsewhere on the project. And if you traverse between those, you're going to see exactly what I'm pointing out here. You're going to see a couple of tenths in elevation. It doesn't have to be that way. So do the QAQC before processing the scan data, or whatever it is that is being done on this project. So once you do this QAQC step and make that check, you have reliable control values, and with the control verified, proceed. Everyone's happy. Now you're looking at deltas down at levels that are expected and tolerable, that is allowable. You've met the project specification. So with the control points and the point cloud agree within the project specifications, everyone's happy. And I'll also mention, if you recall, way at the beginning of the presentation, I said that there were various possible causes for the problem. Just want to mention now that this step has been completed and you have consistent control, it's reliable control. If there are still deltas, differences, you now are in a position to proceed to the next steps needed to find out what the issue is. I'm not going to cover that here, but what I'm leaving you with is the idea that you can't even explore any other reasons for this problem until you've at least determined that the control is good at some level of certainty, and that you've met the project specification. Once you've done that, you've got a job to do to go find out what else possibly has happened. But I think that's much more rare than the problem we've just gone through in this whole presentation of control that is at best within a few tenths. I'm serious. The control, if you do not do a least squares adjustment, you have really no idea how good or bad it is. You just don't even know. And with that, I'm going to just do a little advertising, and this makes me happy, just letting you know of my availability to do training and mentoring staff, management and supervision of projects, and helping develop standards and specifications for projects. Troubleshooting, going in and finding out what happened. I kind of have been doing this for a lot of years, and find the problems and come up with solutions. Solutions that can be done most cost effectively and expedite to getting the project back on track. It's essential. I work on developing customized load distortion projections, and helping people prepare for the next datum that's coming, 2022. And that's how you can reach me. There's my email address. And I've worked on a lot of tunnels, lots of tunnels, and many miles of tunnels. Just pretty large control networks, long corridor networks, really long networks, and developed this LDP for this multi-state project. And even smaller projects like vertical construction. Here's a plan view down. Let's take a look at it from the side, going up stairways and what have you. Small site, but needing very tight tolerances on column locations. And right now I'm working on an LDP from Washington, D.C. to Boston. So that's what I like to do, and that makes me happy, and I'd be happy hearing from you. So thanks for listening, and everybody take care. I think there's more videos to come. Thanks for listening. Bye-bye.